Okay, so this is a rewind of our section 2.2 lesson. Um, so this has to do with rates of change. And so we're going to be finding the average velocity on an interval. And we're also going to find the instantaneous velocity at a point. So let's get started with this. So the function s that gives the position of an object as a function of time t is called the position function. If the object changes position over a period of time, delta t, the average velocity, is given by the following formula. And that's going to be delta s over delta t. That just simply means that we're looking at the change in position over the change in time. In this particular problem, we're given that a tennis ball, it's dropped at a height of 100 feet. Its height s at time t is given by the position function, right? The position function. And it's given. We don't have to figure that out. It's just given, and it's minus 16t squared plus 100. Right off the bat, we need to recognize that this is a quadratic equation. There's that squared term right there. The other thing we need to look at is that this has a negative sign in front of the coefficient. So by looking at that, by knowing those two things, we know that our quadratic or our parabola that the quadratic equation is going to give us is going to look something like this. All right, and that's a very rough approximation of what it's going to look like. So it's going to open downwards, right? Okay, so in this question, in this example, we're told that s is measured in feet, and s is measured in feet, and t is measured in seconds. So we're supposed to find the average velocity over the time interval. So we're going to use this change in position over change in time. And it's not that bad. It's actually kind of simple. So basically, change in position, right? So in order to know what the change in position is, I need to plug in the values for my intervals into the function. We're going to subtract. So we're going to start with the 2. So we're going to take s of 2. And I'm sorry that my s's look like 5s. But we're going to take s of 2, which means that we're going to plug 2 into the position function. And then we're going to subtract s of 1, which means I'm going to plug in the 1 into the position function, and it's going to give me some value, right? On the bottom, what I do is that I put the 2 minus 1 there. On the top, if I plug in a 2 into the equation, so let me write that out here. Negative 16 times 2 squared plus 100. So that's going to give me a value of, let's see, 36. And I'm not doing that in my head. I'm using a calculator for this. So then I'm also going to plug in 1 into that equation. And so I'm going to plug in, let's see, the 1. I'm going to put right negative 16 times 1 squared plus 100. And that's going to be 84. 84. So again, I'm just, s of 2 minus s of t. It's going to be 36 minus 84. I'm subtracting the first number in that interval. Well, that first number from the interval, I plug it into the function, gives me a value. I'm subtracting that from the second interval. Okay, basically it's just 36 minus 84 here. 2 minus 1 is just 1. If I do the math here, this ends up being negative 48 feet per second. So there's a negative value there. Okay. Let's do one more example. I'm going to make this a little bit smaller here. I'm going to move it out of the way. Put it over there. So I know it's kind of hard to read, but you guys should have already written it down. On the second example, we're going to have another interval. And this time we're going to have a 1. It's going to start from 1 second to 1.5 seconds. Again, I'm going to plug these numbers into my position formula here, or function. So let's erase this. I need some space. So I'm going to, and it's going to be, in this case, it's going to be s of 1.5 minus s of 1. And then again, it's going to be not 2, but it's going to be 1.5 minus 1. So again, this is my average velocity. I'm abbreviating here. Okay, so on the top, if I plug in 1.5 into that position formula or function, I get 64. If I plug in the 1, I already know that that's 84. I already calculated that. And then I have 1.5 minus 1, which is going to be 0.5. When I do the math here, I end up getting 40 feet per second. Oh, made a mistake. Forgot the negative sign. There's a negative sign there. All right, so we got two average velocities, right? Negative 40 feet per second. And we got, the other one was, what was that? Negative 48 feet per second. All right, so I'm going to erase this and just put the answers down. So for the first interval, we ended up with negative 48 feet per second. For the second interval, which I erased by mistake, which was 1 to 1.5. On this interval, my average velocity was negative 40 feet per second. All right, so I'm not going to talk about this table at this moment, but remember this problem had to do with the tennis ball and dropping it and stuff. And so by looking at these average velocities, we have a negative 48 and then negative 40 feet per second. The average velocities are negative, which indicates that the ball is moving downward. I know some of you may or may not have taken physics, vectors in physics. If you've taken physics, you know that that vectors can be positive, they can be negative, they can be 0. And also the speed is always the absolute value of velocity. It can't be negative. So if I was looking at the speed for the first interval, it's actually 48 feet per second. The speed for the second one would be the absolute value of that, which would be 40 feet per second. All right, let's look at this graph. I changed the graph that was in the notes today. And so let me pull out a ruler here. And we have to know that average velocity, well, I'm telling you now, average velocity is the slope of the secant line. And if you guys remember secant lines, they're crossing a curve at 2 different points. So if I'm looking, this is a secant line right here. So I have point P here, and then I have this point over here at T2, right? And so that's a secant line. It's touching it in 2 different places, right? So as I make the interval smaller, and here's another point right here, as I'm making my interval smaller, okay, smaller, and finally making that interval kind of get, super tiny, right? Then those secant lines end up approaching my tangent line. So it becomes my tangent line. The closer, or the smaller and smaller I make that interval. And the intervals that I'm talking about are like from here, from here, from here, and from here, right? So as that interval gets smaller, it keeps getting closer and closer to my tangent line, eventually becoming my tangent line. Okay, so now let's go to this blurb that's in here. It says, as we decrease the interval used to find average velocity, we can find the instantaneous velocity of a function at a point. So the limit of delta t as it approaches 0 of s times t plus delta t minus s of t over delta t is equal to the derivative, right? Which is the velocity function. So doesn't this look like when we've been looking at f of x plus h minus f of x over h? Doesn't that look very similar? I mean, we have that funky symbol in the front, but it's the same thing. So we're looking at stuff you guys have already been doing in a slightly different manner. We're putting it to work. This is some physics stuff, I guess, that's going on here. All right, so in other words, the velocity is the derivative of the position function. Velocity is a vector, which means it has direction. That's why in that tennis ball example, it's negative, because it's going down. So velocity can be positive, negative, or 0, and then speed is always the absolute value of velocity, and it can't be negative. All right, we skipped that table. You know what, let's go back and look at the table. Basically, what I wanted you to know from this table was kind of looking at it and then trying to figure out what our average velocity was going to be. So in this example, it says the particle is moving along the x-axis with the following positions and times given in the table below. And it says approximate the average velocity of the particle when t is equal to 5. So 5 is somewhere around here. And I know that between 13 and 20, it's about 16.5, right? About. So it's 16.5. So that's all you need to know about this particular table here. All right, going back to the second page, which I think is kind of interesting. We have a diver. He's on a springboard. Well, he's on some kind of springboard or somewhere, right? He's gonna jump. And so when a diver jumps, when he dives, he actually goes up in the air and then he goes down, right? He normally doesn't just go, just plops over like that. But anyway, they usually go, jump up and then they go down. So the question here, the example states, at time t equals 0, a diver jumps from a platform that is 32 feet above the water. The position of the diver is given by s of t, which is equal to negative 16t squared plus 16t plus 32. Again, this is a quadratic. The quadratic formula will output a parabola that has this basic shape. So the first part doesn't really involve any kind of calculus. It says, when does the diver hit the water? So if we know quadratics, right? Quadratics, when we set them to 0, they're going to give us basically the maximum height or the lowest point, right? And so in this case, the diver, like I said, is jumping up and then down, right? So even this part of this little drawing there kind of looks like a parabola, doesn't it? If I were to do this here, let me do that again. If I were to draw that, right? So it's kind of a parabola, right? Isn't that? Okay. So going back to this quadratic, this guy's going to hit the water down here. Let's change that color to blue. He's going to hit the water down there at some point, and we need to figure out when that happens. So I'm going to factor this position formula. So I have negative 16t squared plus 16t plus 32. And I'm just going to set that equal to 0. Then I'm going to factor it. I need to pull out some common terms. The common term is negative 16. So that leaves me with t squared minus t minus 2 equal to 0. If I divide both sides by negative 16, that just leaves me with t squared minus t minus 2 equals 0. If I factor these two guys out, it becomes t, t minus 2 and t plus 1. I did x factor in my head. Well, no, I didn't. I actually did it earlier. So I know that I put the negative 2 up on top, a negative 1 there, and I knew that my two factors were going to be negative 2 and 1. Remember x factor? Anyway, so let's keep going. So from this point, I know that t minus 2 gets set to 0, t plus 1 gets set to 0, t would end up equaling positive 2, t on this one would end up equaling negative 1. We should know that the negative 1, we should infer that negative 1 is not going to work because there's no we're not dealing with negative time here, right? So the negative 1 can't work, and so the only possible answer would be 2. So when does the diver hit the water? When t, which is our seconds, is 2. So at 2 seconds, this guy splashes down here, right? Woo-hoo, splashes. So anyway, B is asking what is the diver's velocity at impact? So that was, let me go back and label this. That was A. Now on B, we need to get the derivative. So let's take the derivative of the function that's given, right? So we have s of t is equal to negative 16t squared plus 16t plus 32. How do I know that I need to take the derivative? Well, if we go back to the notes here, we're trying to figure out what his velocity is, right? And they've already told us that if we take the derivative of the position function, that is velocity. So over here, I'm going to take the derivative of this thing. Always want to write f. Look, I did it again. Derivative of this thing is going to be equal to, this part is going to end up being 2 times the negative 16, so negative 32. I subtract 1 from the exponent, and that gives me t. For the second part of this, the other term, the derivative of that thing is just 16. T becomes, it becomes 1 minus 1, which is 0. So the t goes away, and the constant of the derivative of a constant is going to be equal to 0. So I'm left with this, and that's my velocity function now. Negative 32t plus 16. And so I can label this as v of t equals that. Now that's a terrible negative sign. Let me fix that. All right, so if I want to figure out what his velocity was at impact, I already figured out that at 2 seconds he's impacting, right? So what if we just plug in the 2 here? So it becomes negative 32 times 2 plus 16. That's negative 64 plus 16, which equals some number, right? Oh, negative 48. Negative 48, right? So my v of 2 equals negative 48, but I need to put down my unit of measurement, right, which is feet per second. That's B. Not too bad, right? Oh. As long as Mr. Martinez doesn't erase it. All right, so that's B. I'm going to move this around here, and we're going to work out C now. Oh, wait, I almost forgot. So they also want to know the speed for part B. So speed is just the absolute value, right? So my speed is going to be 48 feet per second. All right, back to C. So on C, the question is asking, when does this diver stop moving upward and start their descent? Upward, okay. So remember, we're dealing with, in the position function, we're dealing with some parabola. And so we need to figure out what's going on here. We need to figure out when we're going to get a horizontal tangent line. And this is not drawn to scale, okay? But we know that at this horizontal tangent line, that's the max, right, for this particular function. All right, so let's see what we can do here. So in order to do this, then we need to set our velocity function, our v of t, equal to 0. So my function is negative 30, my velocity function is negative 32t plus 16. Man, I'm writing messy. Probably because I'm getting to the end here. Negative 32t plus 16 equals 0. I said it when I set this velocity function equal to 0, which is my derivative, my first derivative. When you set the first derivative equal to 0, it gives you the horizontal tangent line. So I start doing some math here. I subtract 16 from both sides. I end up with negative 32t. I divide both sides by negative 32. I'm running out of space. Oh. All right, so I'm running out of space, so I'm going to continue here. So when I do that, when I divide both sides by negative 32, I end up with t is equal to 1/2, positive because the negative signs canceled out. So what is that 1/2 again? And that's 1/2 second. So 1/2 second. So if I'm looking at that diver again, right? I'm going to go back up here. So at t equals 1/2, then I am right about here. That's about my tangent line. That's my tangent line, my horizontal tangent line, which tells me that's the maximum height for this guy here when he jumps up. So at t equals 1/2 a second, that's the highest point that he reaches. All right, great.